Okay, so the record is on. Welcome everyone to the webinar number 4, organized by EUROfusion on GPU programming. So today we have Francois Courteille from NVIDIA, and Francois is giving us a talk on the introduction of OpenACC. So please everyone, shut down your camera and turn off your mic. And Francois, you can start. Thank you.
Yes. Okay.
We can see your screen.
Yeah. So good morning, everyone. So my name is Francois Courteille, and I'm working for NVIDIA as a solution architect. And I will have the pleasure to, present you an introduction to programming with OpenACC. But before jumping to OpenACC, I will just remind you, how GPU acceleration is working, how you have to port an application. I'm sorry, because I guess most of you there have already done or listened to this kind of presentation, but just in case. Okay, so you see the rectangle with the blue lines. So you have an application and you want to accelerate one piece of this application. So what you do is you deport, you offload the code to the GPU, and so you're creating then an accelerated application where most of the code, as it's shown on the slide, is running on the CPU, and but accelerated is running on the GPU. So what's the difference between the CPU and the GPU? So you see the two square here, where with blue little square the CPU, and in green the GPU, and both are working together to run your application. And you see the main difference is you have a lot of small green squares, just to representing the processing units. And on the left, you have on the blue large square are the cores on the CPU, and you have much more processing units on the GPU than you have on the CPU. So this is one the reason why the GPU is running very fast. The second point is you have a much higher bandwidth inside the GPU than you have on the CPU. And these are two different and complementary architectures. The CPU is optimized for serial tasks. Just trying to minimize latency with a set of cache, where the GPU is hiding the latency by running many threads to overlap memory transfers with processing. So now, how do you program GPU? How you create an hybrid application? So with NVIDIA, this is what we are calling the HPC SDK. So this is a set of tools to compile, analyze, and deploy your application on a system. What you have in this SDK, which is freely available, and I guess which is installed already on the machine you are using, you have a set of compilers. And this is something new, because before we have in the CUDA toolkit, we have a set of components, the NVCC compiler, plus libraries, plus profilers, debuggers. But on the side, we had other compilers, the PGI, the Portland group compilers. Now we merge everything into under a single umbrella, which is the HPC SDK. And so the compiler, the PGI compiler, now are part of this set, and they've been renamed. So PG Fortran is now becoming NV Fortran. PGCC is NVC, and PGC++ and NVC++. But if you were familiar with the PGI compiler before, the old names are still in use. So even if you have the SDK installed, you could still use the old name. I mean, and so you have a set of compilers. I mean, libraries, various libraries for running LAPACK type of solvers within CU solvers. You have the BLAS libraries, FFTs libraries running on the GPU. We have introduced also in this SDK MPI libraries and Nickel and CCL. In fact, we call it Nickel, which is a library of primitives which is heavily used for AI with the AI frameworks. And we have this new product which is called NVSHMEM, which is the implementation of OpenSHMEM on GPU. I mean, to do transfers between GPUs and giving the illusion of a shared memory over a cluster. Now let's discuss a little bit about the programming model. So all those languages, all those tools, I mean, enable different programming models, and we will see a little bit further in the next slides. But the two most familiar maybe are OpenACC. Well, OpenACC we will speak about today, and OpenMP and CUDA, of course. So how to program a GPU? So of course you may use math libraries if you are using already mathematical libraries in your application and replacing the library you are using FFTs, for instance, by the one which is using the GPU. Something which is not mentioned here, and I would like to make this point, is if you have an application which is using heavily BLAS, especially BLAS 3 or BLAS 2 operations, there is a library which is called NVBLAS, which in fact, simply by loading it, will replace automatically the call to the BLAS, whatever from MKL or other library, by BLAS, which will be run on the GPU, and handling also automatically the transfers, the data transfers between CPU and GPU. So it could be a quite convenient way to port and run an application if you're BLAS, if you have an application which is dominated by linear algebra. So coming back to GPU programming, there are three ways to implement an application, and NVIDIA's policy, well, NVIDIA's strategy is try to stick as far as possible to standards, language standards. And as you may know, both C++ and Fortran now are implementing parallel features in the language. And recently with C++ 17, the new extensions, the new features will allow to run easily and efficiency application on the GPU, and simply using the language features. And so you will have a code which will be compatible. And the same with Fortran 2018, where now you have this concurrent new feature clause which has been added to the language, and which could be compiled and could generate code for the GPU. So both are standard and could run on different architectures, different parallel architectures, including GPU now on. The other way is to use directives. And here we are speaking about OpenACC, and this will be the main topic of this today's webinar. So OpenACC is both a programming model and a way to program and offload applications using directives. So the advantage is you are keeping your code intact, and because directives are headed as pragmas, like it's shown here, or comment in the Fortran code, for instance. And you could process iteratively, as we will see later on. And the third way is you could code directly in CUDA, for instance, OpenCL, use the language, all the features, which could be all the architectural features of the GPU to maximize your performance. And to give you an overview how to do it, just briefly, a SAXPY, so a linear combination. This is what is shown on this slide. So where we are computing an array of Z, a vector of Z, being a linear combination between two vectors, X and Y. So if we look at the OpenACC implementation, both Fortran and C, you see that we have added one directive here, a kernel directive in C, to parallelize the loop and have the code executed on the GPU. In the same implementation, but we need to close the block where we, up to recently, we didn't have this notion of block in Fortran. I mean, up to Fortran 2018. Now we have this block extension. And so this is the way to do the operation using the BLAS library here, QBLAS. You see on the left panel you have the main program, and you have the set of calls just on the right panel to run the SAXPY using a library. We could do it in CUDA. Here, this is the CUDA on the left, the sequential version. Here, there's a C sequential version, and on the right, the CUDA C implementation. And here you see the first function here, the SAXPY function, which is decorated with this global, which has the CUDA extension, to tell this is a piece of code which has to be compiled and run on the GPU. And of course, I mean, you have to take care of the data transfer, because CPU and GPU have two separate physical memory. I mean, we will see that there are some improvements later. But here in this model, you have to copy in and out the data to the GPU, and you see that this is making the management and the development and management of your code a little bit more complex. The same in Fortran, so we could use also code in CUDA Fortran. I'm jumping, and you could do that. You could also port code to GPU in Python. And exactly here we have an example of SAXPY using NumPy, and we are parallelizing the SAXPY to run on the GPU. The same way we're using decorators here and using the NumPy compiler. So, and you see that. So whatever the main languages you are using, you could use a directives approach to port your application to GPUs. If we are speaking about C++ code and using the PSTL, so the new parallel standard template library, which is a parallel template library. So you see that now we change simply the transform iterator, and we had an execution policy. And depending on the execution policy, for instance, here we could run it on the GPU. So it's a quite, I would say, straightforward way to port a code with minimizing the modification. So this was a brief presentation, and now we will jump to GPU. of course. I'm sorry for the delay. I'm rather new to Zoom, so yes, I know. I have to share. Oops. Trying to find my presentation where it, here. Of course, it was the last one as usual. Okay, and so now we will speak about OpenACC. So just to remind you of the slight reminder of what we presented just before, the way to port an application, and here we will focus on using OpenACC. So OpenACC, where it comes from, in fact, OpenACC is a consortium where different organizations join their forces to create a standard to port code to not only to GPU, but parallelize the port code to hybrid architectures. So it has been created, this consortium has been created just at the beginning of 2010s. It was an initiative also, well, where NVIDIA was trying to impulse, but joining forces from various vendors, compiler vendors, to have something standard among all the community. And now you have different organizations, academia, also industry have joined the consortium to develop the OpenACC standard. And OpenACC is both a programming model, which is somehow different from OpenMP, and of course, I mean, has a standard with explaining the how things need to be executed by the compiler. So, here is what you see simply is in this C stub. We are adding a pragma. I don't know if you are seeing my pointer, my mouse pointer. Okay, no one is answering.
Yes, we can see.
We do see your pointer.
Okay, perfect. So, and here simply we are adding a pragma, and the syntax is pragma ACC, the same way as when you are using OpenMP, where you do a pragma OMP. And here you have this keyword kernels, where the compiler for this block of code, the compiler will try to analyze and generate the parallel code for the GPU, or could be for the CPU as well. However, as you may have seen in the previous slides, you generate parallel code, but we have two separate memories, CPU and GPU. And so you have to take care of where your data are. I mean, so before starting running on the GPU, you need to bring your data in and copy the results back to the CPU to continue processing. And so you see, you have, would say, two kinds of directives. The one which focus on parallelizing the code, and the one which will take care of the data movement. And here, this is, I would say, a kind of template of an application. I mean, you copy your data and you parallelize your code. And you will see later what those various keywords mean. And this is a way, like OpenMP, which is incremental. You start paralleling your code piece by piece, or you could do that piece by piece. I mean, and you keep one single source, one single branch. And this is interoperable with CUDA, for instance. So you could mix different piece of code compiled. And one goal is try to ensure the performance portability. It's a kind of holy grail of parallel processing. I mean, but this way you keep one code, and you could run it on various architectures. One interesting feature is OpenACC is very, very easy to use and easy to learn, as you will see today. And you are not going away from the C or C++ or Fortran you are using. And so that if you are accustomed with C11 or C14, C++14, sorry, or Fortran up to 2003, I mean, still you will still continue to use the same level of language. There is no reason to learn low-level details of the hardware, which for the starting is true. And after that, I mean, if you want to maximize your performance, you will need, but we will see that in another session, that to think how the hardware is used by the compiler. What does that mean, the various keywords you will add to the directives? One point is you are using same code on multiple architectures. And for instance, when you are compiling now OpenACC code, you could generate various versions, versions in the same binary. You will have a sequential CPU code, and you will have parallel GPU code. So depending on your architecture, you will have still one executable which will run on CPU if you have CPU only, or on GPU. Okay. So who is OpenACC today? Oops. Shoot, I did this. Who is using OpenACC? For instance, the US and the community using Summit is running using OpenACC. So 5 of the 13 car codes are using OpenACC. And the statistics, I mean, you see the number of accelerated apps using OpenACC from GTC. GTC, as you may be aware, is the GPU technology conference. We were, in fact, this set of conferences which are organized by NVIDIA every year. And by the way, there will be a new one very soon, early October, where also, I mean, there will be presentation, OpenACC presentation, but a lot of technical presentation and discussion regarding GPU and the use of GPU. So if you are interested, we could point you to the links where you may get more information and register. And for instance, this is on this slide, what you see,
sorry, I think we are only seeing the edit version of the slides at the moment, not the actual slideshow.
Oh, what happened there? Thank you for stop share. What was happening?
Sometimes PowerPoint opens the presentation to a different window, and Zoom doesn't catch that you want to share the presentation window. It keeps showing the edit window. So perhaps you need to start the presentation first and then share it with Zoom, or share the whole screen.
Okay. I have to say, it's the first time I'm using Zoom for presenting. So, oops. Share screen, no. Yes. Chop. Where is it? Here. do you see my screen here?
Yes.
Yes. So, okay, I will. And now, so you should see a set of applications.
Yep.
Is it what you're?
Yes, we do.
Okay, perfect. Sorry for, thank you for,
No
thank
problem
you
at all.
for telling me. Sorry for this inconvenience. Okay, so, well, so did you see those first slides? I was commenting, I mean, I was
No.
Those
commenting
ones we
those
did
slides.
see.
Okay, perfect. So you see that there are a lot of applications and academic which are using OpenACC. One of the latest is VASP. I mean, this is a chemical code. I mean, and where first there was a CUDA version produced, and then they moved to OpenACC, and they are quite happy, and performance is much better with that. Also, and if we have time, I will speak a little bit about GTC. One of my colleagues did. He did a port with OpenACC, and this is maybe something which could interest you. I mean, in the context of EUROfusion. So you see, there are a lot of applications ported to could be in astrophysics, could be in CFD, and so OpenACC syntax. And I'm a little bit. Oops, sorry. Okay. OpenACC syntax. So it's quite straightforward. You see, you are using a pragma with the ACC keyword, and you are giving so directive clauses. And the same with Fortran, where you insert a comment. Here you have the exclamation mark, which is the mark of the comment for in Fortran 90 and further. And so, well, a sentinel, which exclamation mark and the $sign, and followed by the ACC keyword. And then you give the same set of directives. So it's quite straightforward. Oh. And so we will use in this presentation an example code that you may have seen already. It's a Laplace transfer. So simply we will solve the Laplace equations. And we will warm a room, and here in this room you see a slice of the room. In red the temperature, which is very hot, and in blue the air is colder. And so what we are doing, we are simulating the heat conduction through a plate, a metal plate. And so, of course, I mean, we are solving this Laplace equation, the Laplacian here, the Laplacian operator, and we are using a finite difference scheme for that, where we are computing the second order partial difference with this standard scheme. So we are computing this orange point at here an average of the 4 neighbors in the 2 directions. And the code which will be run or which will be used. So we are using a Jacobi solver. So it's an iterative solver, and until we reach the precision, so we are computing the derivatives, looking for the max of the difference between the old and the new values. And after that, we are copying the new into the old and repeating the process, swapping the arrays. So a very simple piece of code, very easy to play with. And so I'm sorry, because I'm a little bit embarrassed. I have a window that I'm trying to hide it.
We don't see any extra windows.
Yeah, that's the Zoom control window, but participant cannot see it. It's only
and, okay. I find a way to get rid of to hide it. Okay, so and then you when you want to port to GPU using OpenACC, the first step is you analyze your code. This is the traditional optimization steps. I mean, first you look for the hotspots where you have to focus, where you have to work really to improve the performance of your code. And so you need first step you analyze, then you parallelize the hotspot, the most consuming parts, and very important when you are doing this iterative approach, always check for correctness. So if you had on optimizations, and at the end you see some numerical differences, it's hard to step back. I mean, or it takes longer to step back to pinpoint where there was a mistake occurring. And so you optimize and you iterate this process, this cycle. And we will see later, I mean, how to use profilers. So the first construct we will look at is the parallel directive. For those who are using OpenMP, I mean, it's something which has almost the same meaning. So the parallel directive simply marks the parallel region. I mean, the region where you want to parallelize, where you want to apply parallelization, and where you want to offload the code to the GPU. And to parallelize the loop, you had another pragma, which is pragma ACC loop, or exclamation mark $ACC loop in Fortran. And so this means that these loops will be between quotes somehow work share on the GPU, offload to the GPU work share among all the GPU units. Simply, if you are not having this pragma ACC loop, if you are not work sharing it, what will do this ACC parallel thing? It will run parallel, but it will run parallel the same loop, all iterations on all functional units. So it's simply. And if you are paralleling a single loop, so you could combine the keyword, the various codes, and simply say pragma ACC parallel loop, and the loop will be parallelized. So you see that if you have various code made of set of loops, I mean, it's pretty straightforward. And we have some code like Lulesh, some example code, where it's the case, and you have simply to have this kind of syntax to parallelize your application. So, and if this is what I'm saying, if you have many loops, I mean, so simply you had various pragmas ACC parallel loop. And this is the first step to parallelize a piece of application. We will see afterwards that to optimize further, we could be tempted to fuse the kernels here, but we will see that later. So, applying that to our example, we on the outer loop, so the loop on J. So we had this parallel loop, and of course we need to have this reduction clause here, exactly like in OpenMP, because here you see that we are computing the max error over all space here on the J and I indices. And this is exactly the same as for OpenMP. So this is a reduction operation because we are starting from a 2D structures to arrive to only a single scalar value. So we are reducing. And we are telling the compiler that he has to generate a specific operation. So he has to use a specific intrinsic, which is parallelized, which has been parallelized, and telling him this is a max operator, which will be applied to produce the error variable. Yeah, and this slide just what I was explaining to. So when you had this the way that is here when we put the reduction operation, just we tell him to we tell him to generate a max for the all j and I indices. I mean, so the reduction will apply on both set of loops to produce only one value. Here, you could also change the way it is implemented. In fact, in this case, we have a matrix multiply, and we are running this parallel loop only on the most inner loop, and of course parallelizing on the k indices. You see that I and j are not changing, and so we are creating a temporary, and so we need to also to create a reduction. And so we have different clauses, and for different operators, we have for this glossary we have could manage different operators, like in with OpenMP. So addition, multiply, max, min, and also logical or bitwise operators. Ah, okay. I see questions coming. I hear questions coming.
Leo, could you mute your microphone, please?
Hello. We have very young GPU adopters, I understand.
Yeah.
Leo, can you mute on, please?
Okay, now how to build and run the code. So the compiler basics. So so we will still use PGCC, PGC++, and PG Fortran. So, but now also with HPC SDK, you could use NVC, NVC++, and NV Fortran. And so the way to compile and generate optimized code for CPU, simply you had the -fast flag. Another flag useful is -M info flag, just to tell the compiler to report what he's doing. I mean, in terms of transformation, or here, if you say -M info equal Excel, give information about how it's parallelizing for the GPU. When he's parallelizing an OpenACC section. OPT will give information about all code optimization. You could see how he vectorizes, if it's generating SIND operation, and so on. And if you want to have the complete menu, you had simply -info equal all, and you have all information about what the compiler is doing and what he's seeing in your code. And so these are, would say, to start with a small code, that this is what I would suggest here. And now, how we compile for a specific target. So we have this -TA flag, -TA, where you specify some options. And if you want to select the GPU and NVIDIA GPU, you say Tesla simply. So you write -TA equal Tesla. You could write also -TA equal multi-core if you, instead of running on GPU, you want to run parallel on CPU. So the same syntax, the same code, now compiled with TA equal multi-core, will run parallel multi-threaded on a CPU. And the keyword you see managed, dot manage, in fact, you build the code for the Tesla GPU, and you manage the data movement. In fact, the application will manage automatically the data movement, and we'll see later what it means. So for here, an example of the information provided by the compiler on our example. So you see that it's generating. So here, this is the line number where it's generating code. So what kind of pragma he detected, and he's telling that. Giving you with some information, and telling you that he generates a reduction operation, and he says that the loop is parallelizable, everything is fine, and so the second loop met in 74 also is parallelized. So this message accelerator restriction size of the GPU copy of NU and A is unknown. Here, as we are generating the code for the CPU, this is something you don't have to take care of. And now the results. So running on Intel CPU, you see that if we are looking at the serial code as one, running on multiple core, I mean, we speed up by a factor of three over 4 cores. Now we will generate the same, well, we will use the same code with pragmas, but now we are telling the compiler to compile for Tesla and to use to have the memory and the data transfer managed by the system itself, by the application itself. And you see that now we are generating code for Tesla, so generating Tesla code, and he's printing some information, pragma SEC loop gang, and we will see later what does that mean. Still generating a reduction operation, saying that he's also creating some, or he vectorized some loops, and we will see later. And you see in red now, he's telling that he's implicitly copying in A and NU. So he's managing the data movement for you. And also copy the error scalar variables and do the same thing. You see the same kind of messages for the second loop. And now we run this on a Tesla V100. I think this is the same GPU you will use or you may have access to. Now we have a speed up of more than 30. So you see that, and simply using exactly the same OpenACC implementation. So the slide I'm showing here are the slides from a bootcamp, and the purpose of the bootcamp is to let you do exactly this set of transformation. I mean, afterwards, and this is the on-demand demo. So I have finished for the first part. Now we'll start the second part. Oops. So Sorry for the delay. I'm learning. Okay. Do you see the new slide, data synchronization?
Yes, please.
Okay, thank you. Okay. Oops. This is better. So now the second section is to look at the OpenACC data management. So as I was telling you before, the CPU and GPU have both their own physical memory. So, and of course you have more memory on the CPU, but a little bit slower. You have a very fast memory on the GPU side, but size is smaller compared to what you have on CPU. So on most of the systems, I mean, the data transfer between the CPU memory here and the GPU memory is done through PCI, through an IO bus, which is not the case of the system you are using. I think Marconi is a Power 9 based system. And I guess you are using a faster mechanism, which is called NVLink. But whatever the mechanism, I mean, the bandwidth, you see the width of the line, the width here is much smaller than what you have either on CPU and, of course, on GPU. I mean, on a V100, I mean, the bandwidth between what we call global memory on the GPU, the bandwidth between the global memory and the cores here, the CUDA cores, is 900 gigabytes per second. On a CPU, on a Power 9 CPU, I mean, between one CPU socket and this memory, you have something like 200 gigabytes per second, so 1/4. But a PCI bus, it's only 16 or 32, depending if it's a PCI Gen 3 or PCI Gen 4. So you see that when you have to move data, I mean, moving data from CPU to GPU could be quite time consuming. And when you are developing application, offloading part of processing on GPU, you have to think of minimizing the data transfer to benefit from the GPU acceleration. However, the first thing is a tool you may use is what we call the CUDA unified memory, or we refer that to as managed memory. So when we're not using managed memory, in fact, you have two physical and two logical memory systems here. And you have to explicitly move data from one side, from the CPU side to the GPU side, and back and forth. When you have managed memory, in fact, you have only one memory, one logical memory, and in fact, you have pages which will reside either on CPU or on GPU, and will be moved by the operating system. When I say operating system, is in a broad sense, is by the Linux kernel and the NVIDIA drivers. And simply, this is a paging mechanism which is implemented exactly like this is an extension of the virtual memory operating system. And so when you are referring to a data through a pointer on the GPU, and if the data are not there, they will be automatically copied from the CPU to the GPU memory. So with such a mechanism, and it's more efficient, of course, on a system with a fast coupling, like the P9 through the NVLink. And so you have, with such a mechanism, you have to care less about how the data are moved from the CPU to the GPU and vice versa. And this is what we have seen in the first example, some slides before. So how we use this mechanism, I mean, and this is what we have seen. This is the managed keyword you had on your compile line. So when you are compiling with manage, that means that all the heap data, meaning the heap data are the data which are allocated in the heap through allocate in Fortran or malloc in C. Well, and so all those memory will then be managed by the operating system and the driver, and automatic transfer will occur when you will run your code. There are, of course, some limitations, because this, as clever as the system is, it couldn't be as clever as the man. And in particularly, there are no possibility of data asynchronicity. There is no possibility to asynchronously transfer data. I mean, well, you may have this possibility if you are managing by yourself the data transfer, meaning that the overlap between data movement from CPU to GPU and processing is more limited when you are using managed memory. So this is an area of tuning that you could explore using data directives. This managed memory concept first was implemented with the PGA compilers, but it has been recognized as something very important for the ease of porting application, of offloading processing to an accelerator, and it has been included in the OpenMP standard, and certainly will be available in the future as well. So now coming back to our example, I mean, if we want to not to use managed now and switch to data directives, if we compile our example with simply Tesla and not Tesla managed, so we will get this message, if you remember well, that the size of the GPU copy is unknown. In fact, what the compiler is trying to do is he would like to generate the automatically for you the transfer when he's paralleling the loop, but to know how to transfer, you need to know the size of the copy. And in our example, it was not by the compiler, and so it stops. So let's review a little bit now let's introduce the data clauses. So the clauses you could add on your ACC pragma, and you have seen maybe some of them already. So you may use the clause copy with a list of objects, so arrays in our example, which has to be copied in and out from the data region, which from the region which will be parallelized. So you could restrict simply to copy in using the copy in keyword, or copy out, because of course, I mean, not all arrays have to be copy in and copy out in your process. And you may also create allocate a memory on GPU directly. So the principal use is temporary arrays that you need to use in your processing. Array shaping. So how to tell the compiler what he has to copy, I mean, from CPU to GPU and back and forth. So if you are in C, so you start to say, you give the starting index and you give the length. If you are in Fortran, and that could be for multiple dimensions, same syntax. And the same for well, not the same. And for Fortran, you give the starting index, but here you are telling the ending index. So these are different semantics. So please don't be confused. And now, if we want to use directives in parallelizing our two loops, if we are coming back to our example, we had this copy in A array with starting with 0. We are in C or C++, and we are giving the length. So we are well, yeah, that's a good point. This is assuming that we have the array which has been allocated contiguously. So if we are using this kind of syntax, so we assume that the whole 2D array has been allocated contiguously, and so we copy this A and we copy NU, and in and out. And here we copying only NU and we copy out A in this iteration loop. When we do that, we compile and we run. We have this extraordinary slowdown. Now our code is 41 times slower than the serial close. So what is happening? Now we look at the profile. So the next step is to use a profiler. And so you see in dark blue that this dark blue are copy from host to device, H2D, host to device. In a lighter blue, this is device to host. So we see that now the time, we are spending most of the time in moving data from to and from the GPU. Why? We are copying data because we are in this iteration loop. So for each iteration, what we are telling the compiler is to copy data on both loop nests. And one question, of course, is, can we reuse the data? Are we obliged to copy data for each iteration? And of course, the answer is no. So how we could specify how we could manage data? So this is what we call data directives. So now we will specify section of codes where we explain what should be copied and what will be copied from and what will be in the GPU memory. And so the data region, in fact, could, of course, overlap, I mean, the parallel loop sections. Now, I'm simply adding this data pragma, you see, and I'm copying the array and the array NU, simply copy in because it's a temporary anyway. So, and I'm doing that outside of the iteration loop. So now I have a data region which will span all over these different processing regions. And if I'm compiling, you see that now I have this extra comment which are added. Sorry, and I'm copying my array A and my array NU, and you see that at loop level they are not moved anymore. It could be depending on this is with a previous compiler version, but you could see that at the loop level, you could say implicitly copying my array. But it will test if the array resides already on the GPU and use a copy which has been created. And now, doing that, now we have 43 speed up compared to the single CPU. So we are back on the performance race. So what we have learned so far. So we have seen that CUDA unified memory is a very useful tool. I mean, in the sense that you could start porting your code, focusing only on the parallelization. I mean, offloading your code to the GPU. But you need to take care of how much costs the data movement done by the system, in fact. You need to, if you are not using managed memory, then you have to use data directives. I mean, and be careful with data shaping. Generally speaking, moving data at each loop at the loop level is not efficient. So with the OpenACC data region, you could decouple data movement and computation. And I think this is something you need to keep in mind. Now, in a processing, you need to synchronize your data. And so this is why we have this update directive. So in different code sections, you have between different code sections, I mean, you need to exchange information or update information. If you are processing on the GPU and want to continue on the CPU, you need to bring the computed information to the CPU. And this is why we have these update directives. Then you do an update self, and an update self will update the array or the arrays. You could give a set of arrays on the host side. And in the same way, you could update, if you are doing a CPU computation, you could update an array which is on the device side. So, and this is a way to synchronize, exchange information, synchronize data between the CPU and the GPU. So in this example, we update the array A from CPU to GPU here on the device memory. And we are updating array B from GPU to CPU. So this is the example of an example of using update, where you are creating you have created a data region, but for whatever reason here, for instance, you need to checkpoint to your computation to a file. So you are computing your array A, sorry, on the GPU, but you have to write the IO to the you have to write, sorry, this array to save it for later use or to a file. And so depending on the time step, you want to checkpoint it. And so you need to use this directive update, and you could use it in this data region. So we have seen what we call structured data directives, and we have also unstructured data directives because codes are more complex. You have seen that we are working with only one file. Where the point is, when your application and your regions are where your assumed data region could span over multiple files. And so now this is what we call unstructured data directives, where we are defining an entry point and an exit point. And here, the same way, we're using the same clause, and simply in this unit, we are saying, let's say file A.c. We are defining an entry point where the array ABC will be defined, and the data region will end into another routine in another file. So, and this is a quite convenient way to describe the data region. And of course, I mean, data regions could, you could create nested data regions depending what you want. So you may have a different enter data directives with, of course, different arrays. I mean, but they could overlap each other. So, and the when you are reaching the exit point, this is where you are deallocating memory and deleting the data, the temporary you have created, or copying out the data to the CPU, and after that having the memory deallocated. So you have exactly you have the same set of keywords plus one, this delete keyword. So here you create in this in the data region, you create some temporary and you delete them at the end. And here we find the same. You don't have the copy here. You have copy in and copy out. You need to be more explicit. And so we're we're adding two vectors here, and I'm creating the enter data section with copying A and B and creating C, and simply copying out C and deleting A and B. So you see that this is a very straightforward example. So how to compare structured and unstructured? I mean, so that the both, well, they have, well, unstructured, you may have multiple starting and multiple ending points, which makes this construct much more flexible. The unstructured, you could branch across multiple functions, where with data, well, the structured data syntax, you must be within a single function, and and things to think is memory exists until explicitly deallocated, where here the memory exists only within the data region. And so this is an example where you could branch across multiple functions here, we see. And and especially in C++ here, where when you are creating constructors and destructors, you could specify, this is where you with the constructor, for instance, you could then have this enter data to create the entry point, and here in this deallocate array we exit data, and you see that this way, I mean, we have added the unstructured region within the functions. So inside the allocate arrays and the deallocate arrays. C++ struct classes. Well, maybe at this time I will skip that. And we will see that later. I mean, we'll keep that for a more advanced version of the webinar. I will make a pause and see at this point if you have already some questions. Otherwise, I will move forward, just speaking a little further about profilers, and later on how to debug code. And if we have time enough, I mean, just to give you an overview of what has been done parallelizing the porting to GPU, the GTC application.
Thank you, Francois. If you go to the chat box, you can see that we have a couple of questions about.
Let me see. Chat box. Where is the chat box? I'm sorry for. Yes. Well, 15 things. Oops. Did you see?
Yeah. Or otherwise, I can go through if you want. The first question is from Simpa. Sorry, so Simpa, you can unmute if you want. So Simpa is asking, you mentioned performance portability and OpenACC being from a consortium. Are other GPU vendors and AMD mainly supporting OpenACC?
AMD is part of the OpenACC consortium. I haven't looked at what their toolchain, what they're doing. I suspect that they have some tools to handle OpenACC code, but I don't know the details. Better would be to ask AMD, for instance. But I think that I hope I'm not mistaken, but I think they have something to handle OpenACC code.
Mm-hmm. Okay, thank you.
If I remember correctly, GCC OpenACC is correct, and AMD correct. Well, I haven't heard what I know that the very last, well, in GCC still in GCC 9 and 10 now, you have OpenACC, and I think they have implemented fully the 2.6 standard. Well, now we are at 2.7. One of the main thing, and I see someone raising hand. What should I do then?
I think you have the right to unmute Thomas on clicking on the mic.
I just wanted to follow up from the question that I wrote about the GCC. So as far as I understand, for an NVIDIA backend, the GCC 10 supports most of OpenACC 2.6.
Yes.
The implementation is still far from being as good as the one in the PGI compilers, and plenty of codes we can't build with it.
Yeah.
As of GCC 10, as far as I know, there was the work done by Mental Graphics Merged, which gives a rudimentary passability for an AMD GPU, but it will not parallelize on the GPU. So it will run incredibly slowly at best, with the idea that the patch coming, the next version will then include let's say the full version. And as far as I know, this work was funded by the US Department of Energy in order that they have portability, because their next 3 machines will have 3 different GPU vendors.
Yes, exactly.
So there's certainly no working performance capable version compiler for AMD GPUs for OpenACC at the moment, but the DOE plan, or the US plans to try to make something available.
Okay, yeah. This is what I was guessing anyway, so that the thank you, Thomas, for the comment and the information. That what let us say? Okay. The question: what happens under the hood for OpenACC? It's connected to CUDA. No. Well, depending if you would have asked this question in past, that would have. So I'm repeating the question: what happens under the hood for OpenACC? Is it converted to CUDA and then to PTX, or is it directly translated to PTX? Is it possible to see the intermediate code? Well, the question could be longer. The answer could be longer than the question. Yes. Today we are using the LLVM backend. So I could show you the compiling the different steps, different to compile to and use the LLVM backend. But of course, I mean, you could look at the intermediate code if you are using the option keep. Well, what's the option? I'm not using it every day. It's keep whatever. Wait a minute. Keep you could use the keep PTX option. Sorry. Well, yes, something useful. I mean, when you are handling, while using the PGI compiler, well, the NVIDIA compiler, NVIDIA PGI compiler. If you want to know more about an option, I mean, so you type, if it's PGCC, for instance, you can type PGCC. And if you want to have more information focusing on specific options, you type PGCC, the option -TA, for instance, and -help. And you will have all the information regarding this option. And if I'm doing that, you couldn't see my screen because this is a different screen. If I'm doing that, you, well, that keep.
We still see the PowerPoint.
Yeah, this is what I'm saying, I mean, because I won't show everything, of course. Where are these things? No. Oh, I don't. Because you have blah blah blah. Okay, I have to take a note, but or is it with CUDA? Normally, I was looking at the code. I mean, but it is possible anyway. And manual memory transfer. The answer is you could mix, but not on the same array. So the question is, you want to? Okay, the question is, can we mix managed memory and manual memory transfers? Use UVM for convenience, but manual memory transfers for tuning. The answer is yes, you could do that. You could do that. So, but you have to be cautious when you are doing, in fact, so you could mix managed memory and manual memory if some of your arrays are using managed memory, and but you need to be careful. Maybe Thomas, we could speak later on the side what you have exactly in mind and what you want exactly. So just to rephrasing my answer, I say it is better not to try to mix managed memory and manual memory. So in a more advanced mode, you could, but if you're just starting, the answer is try to avoid that. Next question is, on Marconi, we are recommended to use IBM compilers. Well, the answer is OpenACC is not working with the IBM compilers. In OpenACC, can you call function within parallel loops from Simpa? Answer is yes. This is a routine which is called ACC routine, but we won't see it today because but we could see that in a more advanced training. Question from Dimitri: with NVIDIA libraries code like CUFFT distributed mainly in PTX and certain other what is the approach? From scratch. Oops, this one is more complex. It's less a technical question than yes. In fact, ideally what you would like to have is a kind of library which could be used everywhere. So that need to have a kind of standard for tune code between using some low-level open source API. But the first step would be to have a kind of agreement between all the vendors. This is the reason of consortium. So that could be a good idea, but for the moment it's not there. It is a good idea, definitively. Okay, if there are no more questions, then I will speak about profilers. No, I have to go to Zoom. Okay, do you see the slide?
Yep.
Okay. So, and I will focus, you see there are many NVIDIA profilers. In fact, we are at a point where we were changing profilers. And from what France was telling me on Marconi, you are running under CUDA 10.1 and CUDA 10.1, if I'm not mistaken. And you have not made the transition, or Marconi has not made the transition to CUDA 11. Because we have introduced a new generation of profilers. We call that Inside Systems and Inside Compute. Because we wanted to decouple the tracing part from the kernel measurements, in fact. So, and here I will mainly focus on NVProf and the NVVP, which is a visual profiler, the GUI you may use when you want to analyze your profiling results. So as I was telling you, I mean, there are different profilers. The very new ones, Inside Systems, which is the tracing profiler, giving you the timeline more in the same way as NVProf and NVVP was showing, but covering more more sources of information, like Linux system libraries or math libraries, and some more CPU information reported, and so giving you a better view of what's happening in the system, because it's not only the GPU but the whole system you are looking at. And Inside Compute here is the product which is focusing on what happened with the kernel, looking at the hardware counters and giving you information about how the GPU is used. So those information were given reported by the NVIDIA profiler NVProf, and you could display those information inside the visual profiler. You have two other profiling tools. One which is integrated inside the on Windows in the this is a Visual Studio Edition, and one which is integrated. This is a plugin for Eclipse if you are using Eclipse. Well, this is a slide just to summarize the difference between the various profilers here, if you are accustomed, but mainly to outline the differences between the visual profiler and the Inside System and Compute. So here we have a mix of tracing and, as you could see, tracing and kernel information, detailed kernel information reported. Where here we are mainly focusing on tracing, but we are covering a large extent, much larger extent here with an Inside Systems. And by the way, I hope you could, even running on with CUDA 10.1, you could install Inside Systems and Inside Compute on CUDA, and try to use it before moving to CUDA 11. So let's have a quick look on NVProf and the visual profiler. Yes, and before you had also somehow PGProf, who was a profiler developed, maintained by PGI, but now it merged with NVProf. So, but for older version of the tool set, tool chain, you may have PGProf, but let's forget it now. Now, what you have is NVProf, so it's a command line interface tool, which could produce textual output or files, including a lot of data, and those files will be processed with a visual profiler. And it covers, I would say, mainly the GPU side. You could get some information on CPU, kind of flat profile, but all detailed information regarding kernels and things like that will be reported by NVProf. So, in fact, it's a kind of what the Americans are calling a cheat sheet. Here, the easiest way, the simplest way to use the profiling is type simply NVProf and your application line, your application and the options. And behind you will have a set of information displayed, and you could look at what is reported. If you want to use the GUI, then you say that the information is collected and stored into this file. In this case, we call it prof.nvvp, for example. You could give any name with any extension, by the way. So if you have an MPI application, I mean, here we are running with 4 tasks, and we simply prefixing the application launch with the NVProf and storing the information. Here we are storing the information per task using this %h and %p to give the name of the host and the PID name. Or you could use the rank number, for instance, because if you have also access to the rank number because you are running MPI. Oops, sorry. Here you may also collect some low-level metrics. And if you do that, be careful with the -- analysis metrics. NVProf will run many times the application because what you are telling here is to collect all information regarding all metrics. Knowing that you could sample or access to only 4 hardware counters per run, and there are many hardware counters, that means that your application will run depending between 9 to 20 times. So be careful when you are using this keyword. But doing that, you will collect all the information, and you could do a very, very detailed analysis. Well, sorry, with the mouse, playing with the mouse. To avoid, I mean, waiting for hours, you could simply limit the number of times each kernel is run. I mean, here we are telling the NVProf just in this example to collect information about the second occurrence of each kernel. So this is limiting the runtime, the total runtime, and much faster, and give you a very good overview. And if you want to limit the time to profile, simply you limit here for the first 60 seconds in this example. And this is after the GPU context creation, because you could have an application which run, but not use the GPU immediately, maybe 1 hour after starting. And so this information is simply the initial point for counting time is when the first context, the GPU context, is created, the first time the GPU is used. And here is an example of port that if you type nvprof.your application here, you will see so the percentage of time this kernel is used here. So it has been called 101 time, and it's using 95% of the time, 4.7 seconds. Here you see. So you have your different kernels. You have also the other statistics. You have the average time, the mean, and the max. So you see that there are sometimes a big standard deviation between the mean and over between the big standard deviation over all timing measurements. Something important to notice here, these are the copy operations between CPU and GPU. H2D is from host to device, so you are copying from the CPU to the GPU, and memcopy from device to host here. And if you have compiled with the manage keyword, you will get information about the paging and the number of CPU page fault, but GPU page fault as well, and how much time you are spending, to the system, in fact, is spending to transfer data from host to device, and how much time for page faulting for GPU. Let's see. And so basically what you could do as well is to use the visual profiler to mainly look at the timeline of your application. Here you see that this is an example. You see your different operations here, your copy operation here, and your kernel, the compute part, and you have the various rectangle or the different occurrences of your kernel here. And so the first line is summarizing all kernels which are run, and here if you expand this, if you expand the compute, you will see all the kernels behind. And if you could use a guided, you have a guided mode. If you have collected all metrics with the analysis metrics, you could do very deep in the analysis to understand, for instance, the occupancy. How much to see if the GPU is heavily used or not. And what could be the blocker, the road blocker, and why your GPU is stalling, for instance. And this guided mode is very interesting when you are doing fine tuning. Okay, so you could visualize the data movement here. This is what I was outlining. It's a much better view, by the way. Here you have the different kernels. You have the movement and everything now running in one stream, and you see the all things running back to back. Here. You have also the possibility to see what's happening if you are running a GPU, if you are using a unified memory. So now you will have the information how paging is occurring. If it's how much time you will spend in migrating data, on both ways, and give you an indication what you could improve. And something, a very interesting feature when you are doing fine tuning is the kernel profile, and through the looking at the memory hierarchy to see how much memory, how much data you are moving from the various memory level. here you see this is a schematic of a GPU. In fact, you start here on the right, you have the device memories, what we call the global memory, and the system memory, the CPU memory. And you see you have the memory, well, the memory amount coming in and out for each. Everything inside the GPU, everything is still shared in the L2 cache. And after that, I mean, the information data are spread over what we call streaming multiprocessor. And streaming multiprocessor, this is a set of units here where you have this unified cache, the shared memory, and going to the CUDA code, in fact, to be processed. And you have the depending, you see the on the various data paths, you see the amount of data, and you could start understand what's happening at a very fine level to see how your application is using the GPU. But this is not our purpose today, simply to show you that this information could exist. And for a later session, we could look at how the profilers tools could be used to analyze in a very detailed way your application. I will step that. There are many options. Also, you could look at correlating the CPU page fault, for instance. And so for profiling, because time is flying, I will stop here. Do you have questions on profiling? Now I would like to stop here for profiling. I see 2 questions.
I just take the SIMPA question saying, does anyone know if the performance counters are available on Marconi 100? Siri, do you have an idea about that? Maybe you can have an idea. Otherwise, I will forward this question to Chinika.
Okay, I will. There are 2 questions. One is from Dimitri. Dimitri, if you could, is it something which is publicly available on GitHub, for instance? Because Dimitri is stating, I have made an F50 library in Vulkan that works on most GPU and it's just as fast as QA50. I think this is a very interesting thing, very interesting development. Thank you, by the way. And I have another question. What is the current status of parsing do concurrent in Fortran in NV Fortran? Will it automatically map to gang worker vector? Yeah, the answer is it will work as the exactly as the if you had a parallel loop for with OpenACC, for instance. The answer is yes, it will automatically map. Does anyone know if the performance counters are available on M100? M100, it's a Maxwell chip, I think.
I think he means Marconi 100, the Chinika machine, which is why I'm stating that.
On many machines, it's disabled because of the security, or backdoor thing, whatever, the security issue.
Oh, okay.
So here is Serhiy Michalski. I think on Marconi 100 it's the same as on Marconi system. They are not allowed to use these performance counters due to the security issues, as you said, but they are going to implement some scripts which will allow us to use them. But they are still in the testing phase of the scripts.
Okay. So my question is, did you try running or using NVProf and see what is reported?
Yes, I tried to use NVProf, but I cannot say now. It does work, but what exactly, which counters they use, I cannot say. We had just a problem that such software, maybe, liquid, we could not run properly on Marconi supercomputer, and Marconi 100 had the same issues.
Wow. Okay, so sorry for you. That's okay. So I would like. Okay, I think I won't have time enough for speaking about or presenting the GTC work which has been done. I would like to take the remaining time for presenting a little bit or giving an overview of what you could do for debugging, and there are some more questions if there are at the end. So I will go to the last part, the fourth part. Where is that? I did. Ah, yes. Yes, I have to do that. Okay. So debugging OpenACC. So you may have encountered many errors. I mean, some of because you have made a mistake, and but I would say and you see here is the list of errors. Some could be quite tricky. For instance, what is called asynchronous errors, meaning because of course you could run many kernels in parallel, and also you could run data movement in parallel, and then synchronizing properly is extremely important if you want to get correct results. And it's quite you could forget in a complex application to have a weight at the proper place. So there is a weight missing, and so this is a very complex situation where to try to understand what's going on. And I would say there are mainly the first way to think there is an error is because you have a numerical difference within your code. So the question is it justified or not? I mean, is it true that is this numerical difference is coming from a mistake in the code, the way it has been parallelized, or is it normal? Because, and I think you met this situation where you put the code, you have a numerical answer. Sometimes you change compilers, you got a different numerical answers. And the question is it normal? What's a normal between quotes? I mean, could it be explained? And the second type of error, these are the runtime error. I mean, and we will see a little bit further how to handle that. So here I will speak mainly about the numerical I would say numerical differences and other runtime error, which very often you will meet because in running in the output of the run, you will have this information, error 700, illegal address during kernel execution. An illegal address during kernel execution quite often means you are trying to access a data, you have a bad pointer, so why you have a bad address? That's the question. So I'll have to skip. Choop. Yes. So debugging on OpenACC, let's say GPU. So you have first to solve the issue. So if you have numerical differences, there is a mechanism with the compiler, with the PGI toolchain, or now the HPC SDK, which is called PCAST and autocompare. So, and we will see in a minute what is it about. Or you have an illegal memory address or seg fault, or this famous 700 error message. And we will see that we could use PGI environment variable for pinpointing, trying to understand what's going on in the application. So the first debugging tool, I mean, the most universal tool is printf, or print in an OpenACC section. I think this is something that a lot of people are doing still today. I mean, just to print print your data, print the value of your data, just to understand what's going on. So, and of course, I mean, printf could be used, well, of course, not of course, it has been some time before to successfully have a good implementation. But you could use printf in an OpenACC section. That's the point. And this works both for CPU and GPU. I mean, for parallel sections and CPU and GPU. It's the point I wanted to make. So when you have numerical differences, you could use OpenACC PCAST. And what an OpenACC autocompare. So this mechanism, in fact, is you are running the application both on CPU, exactly the same set of instructions on CPU and GPU, with the CPU version and the GPU version, and you are comparing the data, the results. This is a normal way. And you compare your data, and you could you could monitor what's going on, because you could tell you could tell to the runtime if what is the tolerance, how large could be the deviation between the CPU and the GPU. Is it 10⁻⁶, 10⁻⁷, or I don't know what makes what is physically meaningful here. You could tell that. You could tell the runtime, okay, if there are, I don't know, 50 differences, please stop after, because continuing running is meaningless. And so you could monitor what's going on by comparing your data. This is an example here. I'm using I compiled with autocompare, and you have this environment variable where you monitor. You could tell I want simply a summary report. Summary report, not a detailed report. Here the comparison rule is absolute value, and you give I want the unit. It's at the unit. And here you see the results of the run and where in which array and what is different, and for each iteration. And so this is a very powerful to pinpoint where numerical differences are happening, and is this something important or not? I mean, and because you could control the fidelity, you could define what could be important. And here you could look at more detail at the links which are given here about how PCAST and autocompare could do. You could also do a CPU to CPU comparison when you are running, when you are modifying simply on the CPU side. If you have some golden data, if you have some initial results, you could compare them to what is run. And simply here, you are saving the data, the B array on a disk, and you could compare it later on with some previously saved data. So that so this is a very nice feature. And you have a set of environment variables you could use with the PGI SEC now, which will be NV SEC. Also, you could be used with the HPC SDK. I would say two of my favorites are PG SEC time, and I forgot to mention that, or to add that to the profiling section. Saying PGI SEC time equal 1, you will have a report about where you are spending time in the parallel sections, and also how much time you are spending in data movement. So this is maybe the first profiling tool you could start with. PGI SEC Notify is a very interesting mechanism to display what's going on inside your application, because depending on the value you are assigning to this environment variable, you could tracing only the kernel launches or the data transfer only, or both, or the which region exits data region and you are entering. You could look at the wait operation or the deallocation of device memory. And here is an example of using this PGI SEC Notify. And you see that in function we are uploading data, CUDA data, so which device, which GPU, and how large is the transfer. And here we have we are launching CUDA kernels here, and we are getting the information. So it's a very interesting tracing mechanism to understand what's going on during the run of your application. So, and we have this famous 700 error message. And you have another environment variable, which is PGI SEC debug, and you set to 1, and you will get a lot of information, which will certainly at first time will take you some time to understand what's going on. And so we would need to make an example and work with you to help you to fasten the learning. So for debugging summary, I mean, so you have PGI SEC Notify, SEC debug. You could also force. You could force if you have implemented asynchronous kernel launches or asynchronous data movement. You could force everything to become synchronous again using this very environment variable. Just for instance, this is if you have a missing wait, for instance, this is where this variable could be important, because then you will, if synchronously everything works, you know that there is certainly a synchronization missing or not happening correctly. PGI SEC debug equal 1, of course. I mean, and you could also ask to fill some data with some specific pattern. I mean, to force, for instance, some errors. And of course, I mean, you could use if clause and update directives. I mean, inside your code to help debugging. With that, I would like to finish the debugging. It has been very quick, but I would like to finish the debugging overview. If you have any questions about this section, because we are coming very close to the end of the session. So if there are questions regarding debugging or...
Thank you, Francois. We have some questions and comments in the chat. Dimitri just quoted that he would like to exchange with you regarding the Vulkan FFT code. So I'll take care of that, sending an email to you and Dimitri so you can be in touch.
Yeah.
And we have a question from Thomas. So yeah.
Yes, the answer is yes. It's exclamation mark dollar SEC compare.
Okay, thanks. And second one. Okay, sorry. Okay, you did it. Okay, so thank you, guys. Okay, Thomas is raising the hand. Can you unmute it? I think you can unmute yourself, Thomas.
Yeah, I had another question and maybe you jumped over it. You talked about missing wait. So where you have asynchronous but no wait. I had a question where you have wait but no async. Where this is a situation that comes up occasionally, and I just wanted to check if this is legal.
This is a good question.
It works, but I want to know if it's supposed to work.
Well, I would assume yes. That means that it's legal because there is, in fact, there is nothing to wait. So it's kind of no hope because
that's what I hoped. Yeah.
Yeah, the code is generating, but okay, there is only one stream. There are not many streams are used, so the application is going on, computing on then. So I think this case is less harmful. It's not harmful. The other is much more difficult to find when you may have missed, or the code has missed a wait or is missing a wait somewhere.
Okay.
Oh, you are doing an async update.
Yeah. So I want to do asynchronous for all except for one case, and then of course it's easier if I can just say wait in all cases and have it do a no op where there's nothing to wait for.
Yeah. Okay. Oh, I see. Oh, yeah. Well, I don't know why you are joining this webinar because what you are doing is
curiosity.
Advanced. By curiosity. Okay. Well, yeah.
Okay, thank you. Any other question for Francois?
Is it possible you could save the chat window, the content?
Yeah. I did. And
okay. So, we could share or discuss, and yes, I mean you could share the my mail address. I mean if people want to continue discussing or.
Yeah. Okay, thank you. Any question before we close the call? Okay, so I think we are done. Thank you very much, Francois, for this talk. Thank you very much for taking time for us, and many thanks for all participants to come and many questions and discussion we had. So next webinar will be in October. Topic not decided yet. As usual, if you want to address a specific topic, please send me an email and I'll do my best to find a speaker. Thank you, everyone. Bye.
Thank you. Bye.